Okay, so let's get started. And people on Zoom hear me? Okay, so let's get started. So today we are going to continue to talk about transactions, right? So we started that a couple of weeks ago. And starting from this motivating example, right? So I have multiple of this concurrent group of instructions being issued to the same system, accessing the same state of the system. If you're not being careful about how you mix all those instructions together, yeah, you might have some behavior that you don't really want. The thing you really want, right, so it's a notion of how to group those instructions together. Because once you introduce a notion of group, you can start to define essentially the property of that. So formally, what is transaction? Let's try to refresh our memory, right? So first one, we think about database as a collection of objects. So each object has a name, A, B, C, D, all the type of things, right? Could be table, could be tuple, could be value. And each transaction is a sequence of read and write operations, right? Whenever you read something, you read that from database to some objects, right? So in the memory, whenever you read something, you write something, right? So you can start a transaction by having a very special statement called begin, and then you can end the transaction in two ways. Either you commit, just tell the database, okay, all the changes are done. I want you to reflect that right into the database. Or you can abort. You say, yeah, just roll back. I don't want any of this in my database, just roll it back. So either the user can issue a bot, or the system can issue a bot. And then we talk about these four different properties of transactions: atomicity, right, consistency, isolation, and durability. In the last couple of weeks, we have been talking about actually two of this. We talk about isolation, right, to make sure when you have multiple of those transactions running in the system, we want the behavior that is as if only one transaction is actually running in the system. And the byproduct of that is that if your transaction itself is consistent, that is, if there's only one transaction running, right, by myself, I'm going to bring the database from a consistent state to another consistent state. Together with isolation, right, when you have multiple of those transactions running at the same time, your system will also be consistent because you are going to get to a state that is as if all those consistent transactions are being running sequentially one by one. So we talk about these two properties. How to enforce isolation? So there are two different views about this, right? You can take an optimistic view or take a pessimistic view, right? If you take a pessimistic view, essentially before you can do anything to the database, you need to prove to me that you are not going to cause problem, right? The way to do that is by holding the lock, right? You acquire a lock and then you get the permission to change some object. And you can also take an optimistic view, right? In this case, essentially what we are saying is, yes, I acknowledge at some point, I could have this non-serializable behavior. But I will also assume or acknowledge that that's actually very rare, right? So if you ask me to give you a proof, hold a lock every single time before I can do something, yeah, that's probably a little bit overkill. So then what I'm going to do is by take a more optimistic view by saying, okay, everyone just do whatever they want, but before you commit, I will check whether you are able to do so or not. Highly likely, I will say, okay, there's no conflict. I will allow you to commit, and then you are pretty fast, right? Because you are doing whatever you are doing anyway, without holding the lock. If you cause problem, right? So we will say roll back, try again, right? If our assumption that the non-serializable behavior is relatively rare, so we can see the optimistic way is actually going to be faster. But on the other hand, if we are optimistic when we shouldn't, right? When we will have a lot of conflict, but you are taking an optimistic view, you are having a lot of those transactions being rolled back and being aborted by the system. So today we are going to switch gears and talk about these other two properties, atomicity and durability. What are they? How can we think about the theory behind it? And how can we build a system to enforce them? So just refresh our memory about these two properties because we haven't talked about them for weeks, right? So what is durability? So durability and atomicity, the concerns about the system state when something crashes, when you try to roll something back, or when you try to recover something. Essentially, durability says that if the system crashes after the transaction commit, we want all the changes, all the effect of the transaction remain in the database. So essentially, when you go to a bank, right? So deposit your money, and the bank tell you, okay, it's done, right? Your transaction that is committed. You shouldn't worry about maybe the bank lose power, right? Some system crashes. Your expectation is once the system gets recovered from crash, your money is still there because you told me it's done, right? So essentially, if you have transaction look like this, begin to instructions and commit, durability essentially says that if the system crashes at this point, okay, after commit, when you recover the database from the crash, you are going to see all the effect from SQL 1 and SQL 2 inside the system. And atomicity cares about something different. Essentially, it says that the effect of the transaction is essentially all or nothing, right? Either all the changes are being reflected into the database after recover, or none of the changes of the transaction actually in the database system. So essentially, after recover, you will never see something that is halfway done. So one example of this is durability worries about after commit, but atomicity actually worries about what if something happened in the middle. So assuming the system crashes between SQL 1 and SQL 2, the atomicity says that once I reboot my system and recover from the failure, none of the changes from these two instructions, neither SQL 1 nor SQL 2, will be inside the system. Because I can either have both of this, but I haven't run SQL 2, so I don't know what's going, what the result could be. The only possibility that you have after recovery is you need to roll back all the potential changes SQL 1 is making to your database. And second thing is, what if something happened here? That is, you run SQL 2, and you also issue commit, and the system know that you issued commit, but just before the system tell you, okay, I committed, the system crashed. In that case, when you recover from the system, you can actually see two states. Both are okay. Either you see nothing, that neither of the changes from SQL 1 and SQL 2 are reflected, that's fun, or you see everything. You see both of the changes from SQL 1 and SQL 2 being reflected in the database. So both are fun. But what's important for atomicity is that you either see all of them or you see none of them. Okay? You cannot see something in the middle. You can never see the case that after recovery, the SQL 1's change is there, but SQL 2's change is not there. That's not possible. So before we talk about how to recover, let's try to think about what we are actually recovering from. What are the events that could trigger recovery? So, well, there are actually a lot of things, and that isn't always related to system crash. For example, whenever we try to abort a single transaction, so you can need to undo all the changes of that transaction. This is some type of recovery, right? And then, of course, the system could crash. You could, for example, lose your main memory. Someone pulled the plug of the power. When essentially everything you have in the main memory is lost, but your hard drive is fine, right? So, and the recovery essentially means that whenever I reopen my system, I need to redo all my committed transactions to make sure there's durability. I also need to undo all the active transactions that haven't finished to make sure I have atomicity. And of course, you can do system crash with a loss of disk. Essentially, your hard drive is broken, right? In this case, usually when you have a very mission-critical database system, you have some actually another secondary backup, like a tape, something like that, right? Put the data in, then you can read the backup, right? Something like this. So in this course, we worry about this undo and redo operation. Essentially, we want to make sure the changes of an aborted transaction are undone, right? So typically, you have this before image be installed somewhere. We are going to talk about that today. And then whenever you want to undo something, you read that before image. And the change of all the committed transactions, if they are not reflected, you need to redo them. Okay? So typically, you have those after image, right, being stored somewhere. And whenever you want to redo a transaction, you read those and you write it back. So the high-level idea is essentially by keeping logs. Right? Whenever the transaction wants to change something, you try to put some log record, right, in some file. And to make sure when you need that information, you can actually fetch them. Our assumption in this course is we do not worry about the case that the disk is being damaged. Okay? We assume you lose your information inside your memory, someone put a plug, but your hard drive is there. Okay? Your secondary storage is still there. So there are three things we are going to talk about today about recovery. The first thing is about theory. We want to understand if you run certain schedule of your transactions, whether it's really recoverable, because not all of the schedule, when the system crashes, is actually recoverable. Similar to serializability, right? Not all the schedules are serializable. Okay? So here is also not all the schedules are recoverable. And then there are different levels of recoverability depending on how you actually mix those instructions together. And then we are going to talk about another, essentially a very specific way for you to enforce recoverability and for you to enable those recovery. It's by keeping something called write-ahead log. And then if you have time, we are going to talk about distributed commit. We will have those multiple workers. Can you commit them together? And what does it even mean for you to have atomicity when you have a distributed worker? Okay, so let's talk about theory first. So give me a schedule, which is a very specific way that you can mix your instructions together. We can define its recoverability. So essentially, if you have a schedule, we say T1 read from T2 if the following is true. That is, T1 read a value written by T2 at a time that T2 was not aborted yet. Okay? Essentially, your T1 read from T2, meaning that T2 updated that value and T1 read it after it. And at that point, T2 is still there. Okay? This is the definition of T1 read from T2. So given this, you can actually define different family of schedules. And each one of them have different recoverability property. So the first family is called recoverable schedule. Essentially, a schedule is in this family if and only if the following is true. That is, if in the schedule, Ti read from Tj and commit, then we must have Tj commit before Ti. Okay? And here, Ci is the commit time of Ti, Cj is the commit time of Tj. So second family is called avoid cascading abort, ACA. It actually means that if a schedule is in that family, if and only if the following is true, that is, if Ti read X, that object, from Tj, then that implies Tj need to commit before Ti read X. Okay? Here you have this Ri as the read time of Ti like the time that Ti read X. So you have another family called strict schedule. The definition will be long. But essentially it says that if Ti read from or overwrite a value written by Tj, essentially that means if Ti access some data, right, either read or write something that been updated by Tj, then the following need to be true. That is, Tj either need to commit before Ti read and write X, or Tj abort before Ti read or write X. So we are going to unpack those definitions in the next slides. But these are the three different family of schedules. And we are going to see later they have very different property in terms of recoverability. So now let's see the recoverable schedule, the first family. So essentially, yeah, if Ti read from Tj and commit, then we must have Tj commit before Ti. If you think about what the property that this condition is going to enforce, is that if you have a schedule that's recoverable in this family, you have durability in the sense that you do not need to undo a committed transaction. So here's one example. Okay? Assume you have this schedule. You have T1, you have T2, right? They start in the same time. T2 write X, T1 read X, T2 commit, T1 commit. Is this one recoverable? So let's look at this together. Is this one recoverable? How to think about that? The way to think about that is by looking for all the pairs that T1 read from T2 first, right? So here you have the T1's read is actually from T2 because T2 updated this value, and T2 hasn't aborted yet, right? T2 is there. So essentially you have this T1 read from T2, and then you check whether T2 commit before T1. Right? In this case, yes, T2 commit before T1. And then you try to check, okay, is there any cases that T2 read from T1 because the definition is symmetric, right? So whether T2 read from T1, no, T2 read nothing, right? So essentially, for all those pairs that some transaction Ti read from Tj, your condition hold. So this one is actually recoverable. By looking at this, right, you have this read pair, right, Ti read from T2, and then you have this commit. So there's this parallel structure of this, okay? Ti read from T2, but also T2 commit after T1 also commit after T2. Now let's look at another example where that is not true. We do not have this parallel structure. If you look at the schedule on the right-hand side, is this recoverable? Well, clearly it's not, right? So here you have this pair, right? T1 read from T2, but on the other hand, T2 commit after T1. You do not have this parallel structure. And here it's not recoverable. What could the problem that we have when something is not recoverable? In this case, imagine the system crash at this point. The T1 commit, system crash before T2 can commit. What should I do? In this case, because the system crash, I have to undo T2. But to undo T2, I need to undo the write of T2. Because all the changes from T2 need to be, shouldn't be there. I need to recover the original value of X. But the problem is I have a T1 whose result relies on X that's written by T2. If you roll back T2, you have to roll back T1, but T1 committed. So that is a problem. Because we do not have this parallel structure, you have this like this structure that if you look at like from T1 to T2, right? So like you have read and write, right? From the lower part to the upper part, but for the T1 to T2 for the commit, you have lower part, you have upper part to the lower part, right? So you do not have the parallel structure in the direction. Something can happen in between on the commit to make the system cannot enforce durability, because you have to undo a committed transaction. On the other hand, if all of the read-from relationship follow this parallel structure, as you can see, you will not have this problem, right? So this is the family recoverable schedule, right? So as you can see, as long as the schedule is within this family, you have some recoverability property. Any question for this? Any questions so far? No? Okay. And you can make this even stronger. Another family for recoverability is called the avoid cascading abort. As the name implies, it's try to avoid cascading abort. But here is a very precise definition of schedule in this family. So we see a schedule in this family if and only if Ti read X from Tj, okay? Then Tj must commit before Ti read it. That's essentially what this means. So if a schedule is in this family, it actually means aborting a transaction will not cause cascading abort of other transactions. So let's look at why. This is one schedule. Let's think about whether this schedule is, is in ACA or not. So let's look at it together, okay? T2 write X, T2 commit, T1 read. So who thinks this one is an ACA? Who thinks this one is already cascading abort? Who thinks this one is in there? Who thinks this one not there? So to look at it, if I go back to the definition, right? So here, T1 read from T2, right? Now T2 updates something, and T1 read it. And then you try to check, okay, now I have this read-from relationship between T1 and T2. If this schedule is in ACA, it means that T2 must commit before the moment T1 read it. Then I try to check when does T2 commit. So here, T2 commit before T1 read the value from T2. So the condition is satisfied because there's only one pair of read from, right, relationship in this schedule. If there's multiple of those, you need to check all of those. So this one is in ACA, okay? Now let's look at another one. So here, T2 write, T1 read, T2 commit. Oh, I put the answer there already, okay. So this was not in ACA. Why? Yeah, again, go back to the definition. If you check the read from T1 and T2, right? So T1 read from T2, and they'll say, okay, for this pair, when does T2 commit? So here, T2 commit after T1 read, right? That violates the condition we have in the definition. So this one is not in ACA. What could be the problem if one schedule is not in ACA? The way to think about that is to think, okay, now, like assuming the thing on the right-hand side, and system crashes here, what would happen? Before T2 can commit, the system crash. In this case, I have to undo T2. Right? T2 is not done. When I recover, I need to undo T2. But when I undo T2, I need to undo the old value, undo the write on X. I need to recover X to the value as if T2 never happened. But because the current T1 that is still running at this moment relies on the value written by T2, I also have to abort T1. So this is called cascading abort. in the sense that aborting a single transaction, here T2, also implies I need to abort other transactions. Okay? On the other hand, if you have this structure on the left-hand side, that is, the schedule is in ACA, this thing will not happen. Right? What if on the left-hand side, the system crashes before T2 commit? In this case, it's fine, because at that point, T1 hadn't read anything from T2 yet, so T2 can run. Sorry, like T1 can continue to run, even though like you abort T2 at any moment, because T1 only read that value after it knows T2 will commit. So this is the second recoverability family with a much stronger property compared with recoverable schedule. Now, there's another class called strict schedule. So the definition will be long, but if you unpack it, it's actually not that hard. Essentially, it says that if Ti reads from or overwrite a value written by Tj, then the following must hold if you want the schedule to be strict. That is, either the Tj commit before Ti access it, or Tj abort before Ti access it. So essentially, if you have a schedule that's strict, it means that undoing a transaction not only doesn't cause cascading abort, but also doesn't undo the changes of other transactions. Now let's look at one example, right? So here you have a schedule where T2 write, T1 write, and then T2 commit, and then T1 write. Is this schedule strict? Who thinks this one strict? Who thinks this one not strict? Right, so this one strict, right? The way to think about it is, again, very similar to ACA, right? You look at all those pairs that T1 access a value that T2 write before, and then you check whether T2 committed or not. Right? So in this case, it's fun. On the other hand, this is an example that is not strict. Why? Because T2 writes something, T1 overwrite it, and T2 commit. So you have this type of structure. So what's the problem if a schedule is not strict? In this case, again, right? So imagine the system crash here that I need to undo T2. In this case, if you think about it, when you recover, I have to overwrite the changes already done by T1, because I have to recover the value of x as if T2 never happened. That is actually very, very hard to do. In this case, what should be the value of x? Should be the value of x as if, like after T1, or should be, yeah, it's not really clear, right? Whether I should overwrite the value of T1 or not. So if you have something that's strict, you don't have to make that decision at all. So this is the three different family of recoverability. Okay, you have all the possible schedules. Yeah.
Why is it a problem that we need to override T1's write? Because it's arbitrary to begin with whether T1 or T2 writes first. So in the end, it doesn't matter if T2 or T1's write is in the system.
Yeah. So I mean that's a very good question. But imagine T1 continues, right? So, and imagine T2 also access to other values. For example, T2 will also write x, something like that. T1 also, so like T2 have access to some other value like y. T1 have some access some other value z, right? So you need to make sure all those copy of the different objects to be consistent, right? So like if you only look at x, I don't see a problem, right? So if every single transaction only have access to one value, yeah, sure. I mean, either is fine. But the problem is once every single transaction access instead of multiple of those objects, you have those consistent problem, right? Yeah. Yeah. Okay, makes sense? Okay. So we have this multiple family of schedules. Okay, you have all the schedule, right? Some of them are recoverable, some of them are in ACA, some of them are strict, and some of them are serial. Okay, if you run whole thing one by one, you are fun. You are fun always. And we talked about serializability last time, right? You can also put conflict serializability here. It's actually talk about a different dimension of schedules. So the thing that we want is actually we try to enforce this part by default. We want to have something that is serializable or conflict serializable, and also we want something to be strict. And luckily, that region, this green box, is larger than serial schedule, because then you can actually allow some of the concurrency between transactions. So by default, we want the green box. How should we do that? One way to get there is actually by use strict two-phase locking. Okay? So last time when we talked about two-phase locking and strict two-phase locking, right? So we didn't explain why it's called strict two-phase locking. Right? The reason it's called strict two-phase locking is whatever schedule is produced, not only going to be conflict serializable, but also going to be strict. The word strict has a very, very precise meaning. It now means that this one is more strict than two-phase locking. It's because strict is for the recoverability side. So just refresh our memory about this. When you have strict two-phase locking, what you are going to do is the following. You have two different phases in the transaction. The first phase is a growing phase that you can keep acquiring locks of objects. And then in the second phase, right, you keep all the lock until the very end of this transaction. If the x-axis is time, y-axis is the number of locks a transaction hold, you can see you have this growing phase, and then suddenly at the end of the transaction, you drop all the locks. That's strict two-phase locking. So the statement that we can make, the claim that we can make, is if you follow strict two-phase locking, it will only allow schedules that is both serializable and strict. We know it is serializable for sure, right? We talked about that like last week. Every single schedule that can be allowed by strict two-phase locking is conflict serializable, and therefore it is serializable. Why strict? In this case, right, it's actually interesting. The idea to prove that is essentially by looking at this example. That is, if you think about when can T1 have access to X? Because in this case, all the locks from T2 on the same objects are being held until the very end of the transaction. T1 can only have access to X after T2 release the lock. And that will be after T2 either commit or abort. This actually enforces the structure that we saw in the previous slides about a strict schedule. Okay? Essentially, whenever T1 have access to something, it already knows T2 either committed or aborted. Otherwise, it won't get the lock at all because of strict two-phase locking. This is actually the proof idea about why strict two-phase locking gives you something strict in a very precise way. And last week, we'll talk about that, going to give you something that actually is serializable. So recoverability actually matters. Okay? If you talk to people about concurrency control, most of the time, the immediate reaction is, okay, you are talking about isolation, right? But recoverability is actually, equally important because it actually ensures the state in the database is actually correct, right? So the problem with recoverability is actually could be very, very expensive, right? If you have something that's not recoverable, right? So essentially, you have to abort committed transaction, which is, if you think about it, very weird. If something not ACA, right, you could have the thrashing kind of behavior that transaction keep getting aborted because other transaction abort, right? Which is very weird, right? You are being penalized because some other transaction have problem, which is very weird behavior, right? So if something not strict, right, recover from failure is actually could be very complex, if not impossible. So now we understand different family of recoverability. The second thing that we want to understand is actually okay. So assuming we have something that is, let's say, strict, and then assuming the system failed, how can we recover from such a failure? And that brings us to more on the system side. That is, how can we keep track the changes of a transaction such that if system crash, if I reboot my system and recover from the failure, I can undo my transaction or I can redo my transaction because that's not immediately clear how to do that. So here's some assumption we are going to make before we talk about the system side. So we assume our disk is safe, okay? Our hard drive is always there. Even though like you pull the plug, you reopen the machine, your information stored on hard drive is safe. That is one assumption, which is not always true, okay? I mean, it's very easy for you to just smash your machine and the hard drive is broken, okay? So, and then if you recover from failure from that, it's a different process. Here we assume you just lose power. When you reboot, all the information in the memory lost, all the information in the hard drive is safe. That is our assumption. And here, whenever we write something in the transaction, different from the previous one, it will not be reflected on disk immediately because we are going to look at some Venn-diagram structure. Whenever I write something, I write to my memory buffer. This is assumption at this moment, okay? And then I have addition thing called output. Whenever I output, have this instruction, my changes is reflected from the buffer to the disk, okay? So now this is the assumption at this moment. I write to the buffer, I output to the disk. The high-level idea of enable, undo, or redo is by keeping log. So what is a log? A log is a file, right, that opened for appending only. There's no random access in log. It's like a ledger, okay? You can keep adding things to the log, but you cannot do random access there, okay? So log is a file, open for appending only. It's being managed in the same way as other database files, right? So a couple of weeks ago, we talked about heap file, all the type of things, right? Log is just another file inside database. But only property is you do not have random access on logs. You can only have those sequential write, only append, okay? You can have this sequential read, sequential write, and that's it. So, and same as other files, log first appear in the in-memory buffer, and then when you want to flash it to disk, you flash it to disk. It's the same as other type of files. The fundamental question, if you think about this, is actually when to flash a log to the hard drive to make sure we can, like we know for sure that we can recover from the failure. Okay. Essentially, log is a file for appending only. Appending what? Whenever you append something to the log, you are actually keeping track about some record or operations the system is doing. For example, you can append the record to the log file to say start T, transaction T started, for example. You can append another record like commit T, right? You can say about T, something like this. Or you can keep values. You can say in transaction T, right, it updated the value of X to V, right? Something like this. And another operation you can do on logs is you can also flash the log, right? In the sense that whenever you are writing something, append something, you're actually putting all the information in the buffer. Whenever you are flashing the log, you're actually reflecting them to the hard drive. So, and then this is the instruction in our example we're going to use to flash log to the disk. One thing that is to be really careful about is logs are log. They are not the real data. If I append a record saying that update the value of x to v, it doesn't mean that the data is changed. It just means I keep track about what you are trying to do. Okay? If I write commit t, it doesn't mean t is actually committed. You need to actually do that. Log is trying to keep track about things you are trying to do, not actually doing that. So the whole thing will become more concrete when we talk about some protocol. There's one way of doing this called undo login. So it works as follows. I have a whole bunch of transactions running in the system. But if transaction T modifies a database element X, then I will write a log record in the log file saying that transaction T modified X, and here's the old value of X. I keep track the old value of X in the log file. Every single time the transaction T wants to change X. And then I will make sure that this record, the Tx old value, is flashed to disk. The log is being flashed to disk before the change of X is written to disk. Okay? Before the transaction actually changes the X value on my hard drive, I will make sure the log record about the old value is being flashed to disk. If a transaction commits, you will have a commit record in your log, and this record must be written to disk only after all other changes of transaction are being written to disk. So this is a protocol. Let's look at one example. Okay? So here, different from all the transaction thing that we have been talking about, the state of database, the state of the database becomes a little bit more complex. So again, I have two objects, A and B. But I have the in-memory buffer on the left-hand side, the value of A and B in memory, and then on the right-hand side, I have the value of A and B on my hard drive. Okay? On the left-hand side is my schedule. In the middle is my log file in memory. Okay? So let's try to think about how the system works. In the beginning, for example, this transaction just read the value of A into an object T, for example, right? So this is the beginning of this transaction, and in the log, I will write start T. T started. Okay, this transaction started. And then in the beginning, right? So on my hard drive, I have my A equals to 8, B equals to 8, for example. Whenever I'm reading the value of A, you have a piece of A inside the memory, right? In this case, yeah, in memory you have A equals to 8. B, I don't know, haven't read B yet. And then you can continue like this. You can do operations, right, on this object T, right? You multiply by 2, right? In this case, you do not change anything, right? You're just operating on this local variable. And then you can write it back. Whenever you write it back, right, you only change the in-memory version of A. A becomes 16, but you haven't reflected anything on hard drive yet, okay? You are changing your memory. You can and then the moment you do that, you also append a log record into the log to say, okay, transaction T changed the value of A. The old value is 8. Okay? You have this log record inside the log. But at this moment, they are still in memory. Okay? This is a log in memory. Nothing happened on hard drive. You haven't flushed the log yet. And then you continue to read B, right? You operate on B, you write B. Whenever you write B, you reflect the thing in the memory. Then you have another log record like this. Now, assuming I want to commit, what do I need to do? In the protocol, essentially there are two steps. The first one is before this transaction can change anything on disk, the value or the old value need to be flushed out. So essentially, before I can commit, I need to first flush my log. And then everything before this in the log will be flushed to my hard drive. And then I can do my actual updates. Reflect A on disk, reflect B on disk. As you can see, every single time I output A, you change the value of A on your hard drive. Whenever I output the value of B, I change that value on my hard drive. And then you can put a commit record into your log, and then you flush your log. Okay, and then you can commit. So this is a protocol. Okay, so and then let's take a break. When we get back, we are going to talk about at every single step what if the system crashes. Okay, let's take a break. Okay, so let's continue. Can people hear me on Zoom? Okay. Yeah. So this is the undo login protocol. Okay. So it looks a little bit mysterious at this moment, but it's going to become very clear when you see this. You think about what if the system crash at every single step. Okay. So, but if you are doing this undo login thing, during recovery, what are you going to do? Essentially, if you have a committed transaction, because I can only commit before the commit record in the log file is being flushed out to disk. When recover, if a transaction being committed, then the commit record must be inside the log file when I reopen the machine. Right? So they must have this commit record in the log file. And if a transaction is not committed, so for the uncommitted transactions, they do not have this commit record in the log file. If you do not have that, then I think about, yeah, that transaction is not committed. And then what I'm going to do is when I reopen this machine, I will look at the log file. I will look for all the transactions that in the log with the start but without the commit. So those are the transactions that are actually being interrupted by the crash. Essentially, I look at all of those, and then I try to undo them, because they are the ones that I need to undo. If there's only one of those, you can only find one transaction that looks like this. You undo with log. So we are going to talk about how to undo with log. And then you write a abort T at the end of the log after you undo all of the changes from T, then you flush the log. If there are multiple of those uncommitted transactions, what should you do? You need to undo all of them. So when you undo them, is you go all the way from the end of the log to the head of the log. Every single time you see an old value of something that's being updated by the transaction T, you revert the value of the objects to the old value. That is, undo the changes of the transaction. You keep doing this, and then once you have undone all of the transactions that you want to undo, right? You write abort T at the end of the log, and then you flush log, then you are done. So now let's look at this. Let's imagine at every single step the system crashes. In the very, very beginning, okay? What if the system crashed at this moment? In this case, what has been done in the system? Yeah, in the system, the transaction reads something. There's a start T record in the log, and then the system crashed. When you reboot your system, when you restart, what will be in the log? Well, the log is also a file. If you do not flush it, nothing will be written on disk. If the system crashes at this moment, and then you reboot your machine, you are going to see an empty log file. Right? Because nothing has been flashed. Everything is in memory. my log file is empty. Essentially, the system is in a state that as if the transaction T never happened. It doesn't even have the start record there, right? It's as if the transaction never happened, which is true because transaction has done nothing to my system yet. It read nothing. It doesn't change the state of the system at this moment. So when I reopen this machine, I do not even need to undo this T. I don't even know this T existed in the system by looking at the log. There's no start record there. My log file is empty. How can I undo it? I don't need to undo it because it has done nothing, right? So I'm happy, I'm done during recovery. You continue, right? So do something inside the local object T, right? What if system crash here? It's the same. When you reopen the machine, the log file is empty because I haven't flushed it, right? So what do? I do nothing, right? So what if the system crash here? Once the transaction have done something. In this case again, right? When you reopen this machine, you have an empty log file. So I do nothing during the recovery. As you can see, even though the system have changed the in-memory state, because in undo login we have the constraint that is the log file need to be flushed before a transaction can actually change the real state of the database. If you do not see all of those old values in the log record, my transaction has changed nothing on my hard drive. That is like the consequence of that constraint. Because of that, if you reopen a machine and do not see any information from T, you know that whatever transaction was in the system before the crash, they haven't made any changes to my hard drive yet. So to undo them, I can just ignore them, okay? And then what if the system crash here? It actually gets more interesting. Now, I have essentially two of the changes being flashed to my hard drive. If you reopen your machine at this moment, what are you going to see? You are going to see these 3 records in my log file because I flash it, okay? You are going to see start T, and the old value of A is 8, the old value of B is 8. These 3 records in the log file because I flash it, okay? And then the transaction T, they already updated the value of A. As you can see, the value of A is a new value. At this moment, crashed. When I reopen the machine, I see the 3 records in the log. What did I learn? The first thing is, okay, if I look at my log file, I will see the T started. There's start T, but I do not see the commit record for T. So I know something happened, okay? Then I need to undo all the changes from T. What should I do? I will go from the end of the log, okay? Log, I always go from the end, at least for undo login. I go all the way up. I will say, okay, the first thing I read is T, B, and 8. Transaction T changes the value of B to 8. I undo it. Okay, I take that record, then I will update the value of B to 8. In this case, the value will happen to be 8, right? But I just say, okay. I just go to change 8 to 8. Okay? And then I go the other record. I have T, A, and B. Then what I'm going to do is I will go to undo the value of A, also back to 8. I want to undo all the changes have been done by this transaction T. And then keep going. Then I reach the start T. I say, okay, now it's the beginning of the transaction. I have undone all the changes from T. I will write abort T in the log, flush it, then finish the recurring process for transaction T. Make sense? So as you can see, the reason that we have those constraints, that is, you must flush your log before you can actually change the database state is to make sure, before I can change anything, I have enough amount of information in my log to allow me to undo all the potential changes I'm going to make on my database. So what if you crash here? It's the same, right? When you reopen the machine, you see the same log file, right? So, and then you just undo everything. The only difference is at this point, you happen to also change B, right? So on the hard drive. But I don't care. I'm going to read the last log record, going to change B from 16 to 8. I'm going to read the second last log record, going to change the value of A from 16 to 8. Okay? So far, so good. Any questions? No? And now I want to commit. So I put a commit record in the log, and what if system crash here? I'm in the middle of the process of committing this transaction. I was being really unlucky. All the work are done, okay? And now I want to commit. I first put the log record, the commit record in the log, and then crashes. When I reopen my machine, what will I see in the log? How many records will be in the log file if I reopen the machine? Who think we have 4 records? 3 records? 3 records, because log is a file. It will exist in the memory. So essentially here, because I only flash the log once, only all the changes at the point that I flash my log will be reflected to my hard drive. The last commit record, I haven't flashed it yet. It's still in my memory, okay? When I reopen this machine at this moment, I see the first 3 records. So what should I do? It's the same, right? So it's the same as before because all I'm seeing is that 3 records. So my behavior will be the same. I don't know what happened to T. I don't know you are trying to commit T. That information is not there. So what I'm going to do, I'm going to essentially undo all the changes of T. And that is actually why, at this moment, before I flash my log to actually reflect my commit record, you cannot tell the user transaction T is done. Because it is still possible, even though all the changes are already in, it is still possible the system going to undo this T. Because this commit record haven't been reflected to the log yet. You cannot tell the user that this transaction committed at this moment. And then I flash my log. Okay? And the system crashed here. If you reopen this machine at this moment, we are going to see 4 records in the log. And then what should I do? Yeah, then the system knows, yeah, that transaction committed, right? So I do nothing. I do not need to undo the changes of that transaction. So, but there are 2 different kind of scenarios for this case. The first scenario is I flash my log, and then right before I can tell my user I committed, the system crash. Right between the flash log finish and I tell the user I commit. From the user's perspective, I never get an answer from the system. Okay? So the system running, crashed. I never received that signal that this transaction is committed. Then system crash. In that case, when you reboot your machine, system will see this transaction T is committed. Then the user can ask the machine, okay, I had a transaction T. Is that committed? Before you crash, you tell me nothing. Yeah, what's going on? Then the system can look at the log and say, okay, it's actually committed, right? Just before I can tell you, I crashed, right? That's one scenario. The second scenario is You flash the log, you tell the user that you committed, then you crash. And then the user can just forget about the transaction because it knows that this transaction already committed. And then when you reboot your system, all the changes are already on my hard drive. And because the commit record is already in the log, you will not undo the changes of the transaction. So as you can see, right, so by just going through what if the transaction crashes at every single step, the protocol of undo login starts to make sense. Before I can change anything on my hard drive, all the information that allow me to undo those changes need to be flushed out on my hard drive from my log file. And before I can tell a user that I committed, I need to have this commit record flashed to my hard drive. That all start to make sense because I want to undo stuff. Any question about the protocol? No? Okay. What's the problem of undo login? First one is correct, it's great. But there could be something we can improve. So let's think about the amount of data movement that we need to conduct before your transaction commit. What do I need to write? We need to flush out two things. We need to flush out all the changes that this transaction tried to make on my database. And then also, I need to flush out all the logs. This is the amount of data movement that I need to do before I can commit a transaction if I'm using this undo login. This can be expensive. Why? Because if you think about this, the size of the log is for every single update, I need to change, so I need to keep the old value. The size of the log is almost as big as the size of your updates. This makes every single transaction more expensive before I can commit because I need to write more things to the log. The log is pretty big. Can we do better? Now I want to twist this protocol in a way that I do not need to have this additional I/O before I can tell my user I committed. What should we do? So an alternative way of doing login is instead of undoing all those uncommitted transactions, I try to redo all the committed transactions. And that gives you an alternative strategy called redo login. The hello idea is inside the log. I do not keep the old value because I'm not trying to undo anything. I will keep the new value that you want to write. I will write a log record T, X, and new value. And the protocol looks like this. If T want to modify a database element X, I just write this record in the log file. Before T can modify anything on the hard drive, and then I just flash logs and the commit record to the disk. So now let's look at this using one example. Okay, let's do the same thing. In the beginning, this transaction read something, also put the start T record in the log in my log file. Keep doing things, right? Yeah, nothing happened. Keep doing this, keep doing this, keep doing this. And then the only, as you can see, right? So in the log file, I'm keeping the new value 16, not 8, not the old value. At this moment, the transaction knows, okay, everything's done. I've done everything. Okay, finished. And then I will say, okay, I put a commit record in the log file. Then I flash it. I flash all the new value and the commit record in my log file to my hard drive. Then I commit. Then essentially at this moment, the system tells the user, I'm done. Okay? And then after that point, the system can update other things. But system will actually tell the user I committed right after it's flashed the log. It will not wait for the actual updates of the database. Essentially, the system will actually commit at this point, tell the user, okay, I'm done. Okay? Once the commit record is in the log file, the system will tell the user. And this can do whatever it wants. Make sense? They redo login. What happened during recovery? Well, the first case is you reopen the machine. You do not see the commit T in the log file. What does it mean? It means that for this transaction, I haven't told my user is committed. Because before I can tell the user I committed, I need to flush my log with the commit record. So if I do not see that in my log after recovery, like during recovery process, this T is not committed yet. What should I do? Well, I do nothing. Because all my actual change of my database need to happen after I flush my log. So if you do not see commit T in my log file, it means that this transaction hasn't changed anything yet. So I do nothing. Okay? If I see a commit T in the log, it doesn't mean all the changes are on the disk. Because what I'm going to do in redo login is I will flush my log first, and then I will do in whatever updates. Okay? Even though you see the committees in the log, it could be there are some changes from transaction hasn't been reflected yet. So what should I do during recovery? I will redo the change of T. What should I do? I scan the log from the head to the end as a direction. For every single record, TXV, I update X to V, to the new value. I redo the changes of all the committed transactions. That's why it's called redo login. And then for each incomplete transaction, without the commit record, I just write about T. Okay? Now let's look at this example. Try to simulate what would happen if the system crashes. Now we are going to go the other way around, okay? From the end to the bottom. What if the system crashed here? When I reopen this machine, what would I see in the log file? First of all, how many records I'm going to see in the log file? Who thinks it's 4 records? 3 records? 4 records, right? Because when I flush my log, everything before it is going to be on my hard drive. I have 4 records in my log. I see this commit record there. So what I know is, okay, this transaction committed. Okay? I may already told the user, I may not, but this one committed. But I don't know whether all the changes are reflected or not. Because in redo login, I have no control on when the actual change will be there. So just look at this example, right? So the system crashes halfway, like in the middle of the system try to reflect the actual change. If you reopen the database, you are going to see an inconsistent state. A is 16, B is 8, right? So it's not consistent. What I'm going to do is this transaction is committed, so I'm going to redo it. Okay? I'm going to, from all the way from the top to the bottom, I'm going to scan all the record, start T. Okay, great. The first one, the new value of A should be 16. I read that record, I update A to 16. In this case, A is already updated, so I just change 16 to 16. Nothing happened. Okay? And then I scan the second record. I say, okay, this T will change B also to 16. Then I will update the on-disk state of B to 16. Then I see commit T, then I know I have finished redoing this transaction T. And then after that, my database will be in a state 16, 16, which is consistent. Make sense? I redo all the committed transactions instead of undo all the uncommitted one. What if the system crashed here? When I reopen this machine, how many records do I see in my log file? Who think is 4, 3, 2, 1, 0? Okay, I see nothing there. It's an empty file because I haven't flashed anything yet. Okay, there's nothing there. Okay. So what should I do? I do nothing. I know this transaction hasn't been committed. I don't even know there's such a transaction in my log file, right? But luckily, you will not do any changes before you flash a log, which means that if the log hasn't been flashed yet, this transaction make no changes on my database. So I do nothing. Ignoring this is equivalent of undoing whatever. It hasn't done anything yet, right? What if the system crash here? It's the same thing. Reopen the machine, I see an empty log file, right? I do nothing. What if the system crash here? Yeah, same thing. I see an empty log file, right? So I don't even know T exists in my system. When the user asks, oh, what happened to T? You tell the user, yeah, T is not in my log file, so abort it. Since it happened in the middle, it has been making no changes in my database. Try again, right? You can just tell the user the state of the transaction by just looking at the log file. What would the problem of redo login, right? I mean, building systems, right? Pretty much every single problem has every single method has a problem. What's the problem of redo login? So one problem of redo login is the log you are keeping could be very, very long, because you have to redo all the committed transactions. There could be a lot of those, right? So, and you need to keep all of them, because in principle, you have to redo all of them. Why? Because having a commit record in redo log in the file doesn't mean all the changes are done. The database needs to redo from the beginning of the log. If you have a database running a bank since 200 years ago, there's no database back then, like 30 years ago, right? Continue running a database. In principle, you have to redo all the changes, right? Because having a commit record in a log file means nothing. I mean, it means something. It doesn't mean, but doesn't mean all the changes are in the database. There could be potential solution for this. You could have a checkpoint, right? For example, every day, I just have this 10 minutes to say, okay, now everyone just flash out your updates, and then I can ignore, and then I have one checkpoint in my file, and then next time when I recover, I only read it from the checkpoint because I know all the changes are in. Only thing to be careful is if the system crash during checkpointing. That could also happen. Okay, that's another layer of complexity. So there are more in the textbook. But there's another interesting thing that we should look at. Is now we have this undo login and we have redo login, right? Yeah. Yeah.
If the commit always fails at some point because there might be an error, then we have committed some changes already. Then how can we get back the old values, since in the log there are only the new values? So maybe after 10 tries, we just want to never do this.
So what do you mean commit fail?
So in the middle of the commit, it results in error, and then this.
So have I flashed the log yet?
Not yet, no.
Okay, so I haven't flashed my log, and then I try to commit, and then the system crash.
Yeah, but it always crashes. So when we redo all the transactions via the log, then it will still always crash. So maybe after a few tries, we just want to get back.
No, it doesn't work that way. Okay. So imagine this. You are running something. Before you flash the log, you crash. When you open the machine, you see nothing in the log. Right? So you will not do anything at all. So I think your scenario is you do something, you flash the log, I try to commit, then I crash. You reopen this system, you have this log file with the commit record. You say, okay, I need to redo it. And then I try to redo it. During the redoing process, I fail. And then when I reopen this machine, I see this log, the same log. I continue, I do the same thing, I keep doing. Then you probably call your IT to see what's going on. Why the machine keep failing, right? So there must be something wrong with your machine, right? But in principle, all the information are there. You need to fix your machine, right, to make sure it doesn't crash when updating those values, right? Yeah. Or you can copy the log file to another machine, copy the database to another machine, try again, right? All the information are there. Make sense? Yeah. So failing during recovering is very important, okay? So there are a lot of things in the textbook because that can make things really complex. Also, failing during checkpointing, right? So, the system can fail at every single moment. Okay, but there's a trade-off between undo and redo, right? So essentially, we are doing undo login, right? So your data written to disk before your commit is flashed to log. For essentially, potentially have more I/O before commit. For redo, all the modified data in the buffer, right? So essentially, like you do not reflect your updated data until you flush out the commit. So, and also until like you actually commit. Potentially, you have a larger buffer because you are keeping more things in the buffer. So that's actually one trade-off. But on the other hand, right, during recovering, right, so which one is faster depends on whether you have more uncommitted transaction or whether you have more committed transaction. Also depends on your frequency of checkpointing. There is a small caveat about redo login. Because whenever we are thinking about this redo login, right, we always think as if when I flash out my log or making changes, I can actually change the value of a single object. But that's not true, actually, if you think about it. Redo login cannot make any change to disk before the commit record is done. Okay? So that is what we need. But what if you have transaction 1 make some changes on A, transaction 2 make some changes on B, but A and B are on the same page? Because we are dealing with a hard drive. I do not have the luxury to actually updating a single object. Every single time I reflect a change, it's always a page from my buffer manager to my hard drive. What if both A and B are on the same page? Oh, that could cause problem, because when T1 commit, if we flash out the change on P, then I will also flash out the change from T2. And then that will cause problem because T2 hasn't committed yet, but all the changes are already there. This will actually cause a problem. Because, yeah, I mean, this clearly will cause a problem. That break my protocol simply because the structure of my file system. I can only read and write in blocks, not a single object. We also need to handle this part. How should we do that? The way to do that is another login protocol called undo-redo login. That's kind of combine these two different login protocols. So essentially look like this. Before modifying any database element in X on disk, I write a record to my file containing both the old value and the new value. Okay? This allows me to either undo it or redo it. Okay? Then I can pick. I have flexibility now. And then you flash the log before actual changes are made on disk. Okay? That's what we are trying to do. This is one example. In this case, it's the same thing, right? Whenever I'm going to write A, right, in the third line, right, I will also say the old value of A is 8, the new value is 16. Okay? You continue to do this, and before you want to make any changes on your hard drive, you flush your log, okay, to make sure you have all those like values. Then I don't control anything. Okay, so if you want to commit, you want to update your thing, right? Yeah, you can do that in the middle. It doesn't really matter. Okay, or you can flush your log. It doesn't really matter too much at all. If you reopen this machine during recovery, if you see a commit T record is not in the log, you assume you should abort this transaction. What you are going to do is going to undo them. If you see the commit record is in the log file, you say that's a complete transaction. I'm going to undo them. So I'm going to redo them. Okay? So essentially, you test the state of this transaction depending on whether there's a commit record in the log file or not. If there's such a thing, you redo. If there's no commit record, you undo. Okay? That's actually the hybrid strategy between undo and redo give you actually more flexibility. Okay? So this is 3 login protocols. You're putting them together, and also together with what we have been talking about in the last couple of weeks, you get these 4 different properties. Now we can enforce atomicity and durability during crash by keeping logs. We know how to enforce isolation and consistency by holding logs. Okay? So if you are doing strict 2-phase login, combine everything we have been talking about, you have a very simple system, give you this 4 property of a transaction. So in the last 8 minutes of today, let's try to start by talking more like a challenge, and then we are going to talk about solution next week. Not solution, but how people were thinking about that 40 years ago, maybe. One very baseline solution of that. So and that's about distributed commit. So far when we talk about commit, when we talk about transactions, we always think about, yeah, you have one machine, you have one thread doing stuff. Whenever you are mixing things, I'm running instructions one by one. But what if I have multiple of those workers? What if my data is distributed among multiple things? In that case, the query processing becomes interesting, but also the commit protocol becomes interesting. So imagine you are building, for example, Priceline, okay, building this website. If you look at what functionality you can have here, right? You can book hotel, you can book flights. There's still a functionality called a bundle. You can book your flight and the hotel together. Then you get cheaper. If you think about what you are trying to do there, it's by doing the bundle thing, you are actually have some database dealing with hotel, some database dealing with flight, some database, for example, dealing with cars. Okay? There's 3 different databases hosted by potentially different companies. But Priceline, if you look at this portal, right, they try to book all of them for you. You say, I book a bundle, I book hotel A, I book flight B, I book the car C. If you are a user using this functionality, what would be the contract? The contract would be, I have atomicity of that transaction. That is, either you book me nothing and tell me, or you book me everything. I do not want to be in a state that I fly to B, but I don't have hotel or cars. Anything that's not all or nothing, I do not want them. But all of this information are in different places. There's some company dealing with car, some company dealing with hotel, some company dealing with flight. So what should I do, right? The only thing the portal can do is to say, talk to the hotel database, book me this hotel, talk to the flight database, book this flight, talk to the car, book this car. And what if the system crashed like this? That is, during the process of booking the hotel and flight and fun, okay, the whole thing is booked it. And then whenever I'm booking the car, the system crash. And only that database crash. The other two databases are fine. In this case, you are enforcing atomicity for each of those sites. Each of those databases are actually atomic, right? It's all or nothing. The changes of the first two are in. The change of the third one is not in. It's atomic. But if you look at the whole transaction from the portal side, it's not atomic because only two changes are in, one is not. From the transaction level, from the global transaction level, it's not. From the local transaction, it is atomic. It actually means that the local atomicity, when you have multiple databases, doesn't give you a global atomicity. When you have distributed transactions being distributed at different sites, you need to be really, really, really careful about what to do. And it is just a very, very hard problem. So this is a paper back in 2004 about transaction commit among different data sets. If you look at the author, it's Jim Gray and Leslie Lamport, okay? So if these two guys are writing one paper, that is how hard this problem is, okay? So at a high level, what should we do? How can we design a protocol of distributed commit? At a high level, right? So you can have something called two-phase commit, which we are going to talk about next week in detail. The high level is like this. You have a coordinator, which is the portal side, that knows the global transaction. It actually asks everyone to vote. It says, okay, for each of these sites, do you vote for me to commit this global transaction or vote for me to abort this global transaction? In this case, ideally, if the first two databases going to vote yes, I'm done. Okay? If you want to commit, from my perspective, you are fine. The third one, if the third one is still alive, is going to vote no. This transaction actually, I didn't do anything. It failed in the middle, right? So if you ask me, I would vote for this transaction to be aborted. Then the global worker, the coordinator, going to collect all those votes. If any of those sites, the local thing, vote for no, then the global transaction will be aborted. Okay? Then the global one will also ask the local one to abort. If everyone votes yes, then the global coordinator going to ask everyone to commit, because then it wants to commit this global transaction. So it seems very simple, right? But it's actually very hard because first one, even the voting phase, some of the database will crash. If you ask them to vote, they will not vote because they cannot hear you, right? And also, as you can see today, the system can crash at every single point in the process. It can fail in the voting process, it can fail in the committing process, it can fail even some message get lost in the network, right? Then someone doesn't really hear you, right? What can you do? So there's a very, very complex protocol that we are going to talk about next week. So that's all we have for today. I'll see you guys on Wednesday.